Okay, we're now looking at the last question in the assignment on rotational kinematics. So this one says the Earth rotates west to east. So west to east. Yep. It's a solid sphere, and its rotational inertia is given by this. So that's the rotational inertia of a sphere. The mass of the Earth is 5.98 times 10 to the 24 kilograms, and its radius is that. A jet plane produces a maximum thrust of 200,000 newtons. If you attached 1,000 jet planes to the ground on the equator, all facing the west, and ran the engines full blast for a day, would the length of the day increase or decrease? Okay. So they're facing to the west. So they're going to be pushing it. So hold on, the Earth will rotate east to west. The jet planes are all going to be pushing the Earth to make it spin towards the west. So Earth spins west to east. So it's going to reduce the day, the length of the day. So they will apply a torque that will oppose Earth's spin. So the day would get longer. Okay. So we can say angular velocity would decrease. Okay, now the challenge is, what will be the change in angular speed after 24 hours? So we need to work out a few things here. So we have t is 24 times 60 times 60. Omega is, we'll go through 2 pi radians in 1 day, 2 pi over 24 times 60 times 60. That's omega I. Omega F is what we're trying to find out. And then what else can we work out here? We know that the force and therefore the torque that's being applied. So we can figure out, and we know the rotational inertia, so we can find alpha. We need to calculate, and then we can find omega F. Okay, so let's calculate alpha first. So tau, we had 1,000 jet planes, each one producing 200,000 newtons, so it's F times D. The distance from the center that we're applying it is the Earth's radius. So that's going to be equal to 200,000 times 1,000 is 200 million. So that's 200 newtons times the Earth's radius, which is, we were given 6.67 times 10 to the 6. I'm not sure that's actually quite right, but we'll work with the number that we were given. So the torque here is 200 million times 0.67 times 10 to the 6 gives us what's that? 3, 6, 9, 12, 15. 1.334 times 10 to the 15. And that's Newton meters. And then we know alpha oh, I alpha should be equal to the torque. So let's find I first. So I, well, we were given an equation for I up here, 2/5 mr squared, 2 over 5 times, we were given the mass is 5.98 times 10 to the 24 times r squared, which was 6.67 times 10 to the 6 squared. Okay, so that's 2 divided by 5 times 5.98 times 10 to the 24 times 6.67 times 10 to the 6 squared equals 1.06 times 10 to the 38. What was it? It was 1.06, okay. Times 10 to the 38. Whoops. Let's make that a bit neater. 10 to the 38 kilogram meters squared. Okay, that's a very big rotational inertia. And now we can find alpha. That should just be equal to tau over I by our equation. Tau equals I alpha. So that's equal to 1.334 times 10 to the 15 divided by 1.06 times 10 to the 38, which is 1.334 times 10 to the 15 divided by 1.06. I'll write 417 times 10 to the 38, which will give us a very small number, 1.25 times 10 to the minus 23. And that's radians per second squared, which is a very small angular acceleration. And now we can find omega f. So we know that we want an equation that has alpha, t, omega I, and omega f. So we go omega f squared equals omega I squared plus 2 alpha. No, we didn't want that equation. Sorry, that's the wrong one. So we want theta. No, we don't want theta either. We want omega f minus omega I over t is equal to alpha. Okay, so just to save us some time, because it's actually asking us for the change in angular speed, what we'll do is we'll just call this top here is just the change. We can just say alpha is equal to delta omega over t, and then alpha times t equals delta omega, and let's find out what that is. So alpha was 1.25 times 10 to the negative 23. And we want to multiply that by the time, which was 24 times 60 times 60, which will give us times 24 times 60 times 60, which gives us a change of 1.08 times 10 to the minus 18. Radians per second. So not significant. It's tiny, right? And also there would be a problem with it in that it wouldn't really work, because in order for a jet engine to push forward, it has to push air backwards, and the air would then also decelerate. The air moving the opposite way would decelerate the Earth again. So air pushed back by jets would counter the forwards push. Of the planes. So you might get a bit of a wind going the other way, and that wind will kind of cause friction against the Earth's surface and slow it down again. So the overall effect wouldn't even be this, it would be even smaller.